Okay, so in previous chapters, we've been looking at electric potentials and fields in the presence of conductors and point charges. In this chapter, we're going to start to look at electric potentials and fields in insulators or dielectrics. So let's first look at what a dielectric is. So a dielectric is an insulating, which means non-conducting material. So electrons in dielectric materials are attached to the atoms. They're not free to move about. Unlike for a conductor, electrons in a dielectric are not free to move about in the material. So we know we've already studied conductors, and we know the response of a conductor when placed in an electric field is the movement of the electrons or a current. The response of a dielectric when placed in an electric field is the formation and alignment of dipole moments. So here we have a dielectric and the electric field between the plates of the parallel plate capacitors. So these two are parallel plate capacitors. Here's the dielectric. The electrons can't move around, but we do have these dipole moments that are formed, and they're going to be aligned with the electric field. So we're going to look at, start by looking at the response of just one atom in an electric field, and then we'll progressively get to the whole material's response to being in an electric field. So we're going to look at a simple model of an atom, a neutral atom. That's just a positive point charge in the center, which we can call the nucleus, and a negative uniform sphere, kind of like an electron cloud, and the sphere we're going to give a radius A. So that's what we've modeled over here. Here's our nucleus. Here's the cloud of negative charge that has a radius A. So what happens to this atom in the presence of an external electric field? So let's say we apply an electric field in this direction. What's going to happen is that the cloud, the negatively charged cloud, is going to move in the opposite direction of the electric field, and the nucleus is going to move in the same direction of the electric field. So the result is the nucleus is going to be displaced a distance d from the center of the sphere. So we have what's called a polarized atom. Okay, so the electric field induced a dipole in the atom. We have more positive charge on one side, more negative charge on the other side. So the atom is now polarized with a dipole moment in the same direction as the electric field. So here's our dipole moment is equal to some constant alpha, the atomic polarizability, times the electric field. Okay, so now we want to find alpha, the atomic polarizability. Okay, so the equilibrium position, once we apply the electric field, is going to happen when the electric field E is equal to the electric field produced by the electron cloud that I'll call E sub, big E sub little e. Okay, so when the electric field that we apply is equal to the electric field that's due to this electron cloud at this point where our nucleus is. And luckily, we have already found the electric field inside a uniformly charged sphere using Gauss's law. We found that in lecture 2.2. And this is what we found, if you remember, 1 over 4 pi epsilon naught q over r naught cubed. R naught was the radius of the uniformly charged sphere times r. So it was linear with r when we're inside the sphere. So in this case, the electric field due to the electron cloud, if we're a distance d away from the center, is going to be 1 over 4 pi epsilon naught q over a cubed, so that our radius a times d. And I think this should be a E sub E, not E sub A. So at equilibrium, the electric field, the applied electric field has to be equal to this electric field due to the cloud at this point right here, distance d from the center. Okay, so I just rearranged that a little bit. P is QD, is the dipole moment of our physical dipole. So we have E is equal to P times 1 over 4 pi epsilon naught A cubed. So we can rearrange, get the dipole moment is equal to this something times E. We can compare it to what we had before. We wanted to find this alpha. So we find the atomic polarizability to be 4 pi epsilon naught times A cubed, A being the radius of the electron cloud. I'm going to multiply by 3 over 3, multiply by 1. So I can get a 4/3 pi r cubed, pi A cubed, 3 epsilon naught. So if I write it like that, I see that the first term, 4/3 pi A cubed, that's just going to be the volume of our atom of radius A. So our atomic polarizability is just going to be the volume of the atom times 3 epsilon naught. And there's experimental found values for this alpha. For hydrogen, that's what this value is. And for lithium, we have these values. So we found that an atom's response to an external electric field is the polarization of the atom. The atom becomes polarized with the dipole moment that is proportional to the external electric field. Now we want to know the case where we have, instead of an atom, we have a molecule. Okay. When we were looking at the atom, we were assuming spherical symmetry. So no matter what direction we applied the electric field, we were going to get the same response, the same dipole response, because of the spherical symmetry. This isn't going to be the case always for a molecule. The dipole response of a molecule may be different depending on if the electric field is applied parallel or perpendicular to the axis of the molecule. So let's take the example of a CO2 molecule. Okay, so it has, here's the axis of the CO2 molecule. The polarizability is going to be different if we apply the E field along this axis as opposed to perpendicular to it. And in this particular case for CO2, our alpha is greater when the external electric field is applied parallel, this guy right here, to the axis, as opposed to applying the electric field in a perpendicular direction. And the alpha is less. Okay. So in the general case where we want to just have some general molecule, any molecule that has no particular symmetries, the dipole moment is going to be equal to alpha times E, and in this case, alpha is called the polarizability tensor. So the equation looks like this. So, for example, in a spherical symmetry, if you apply an electric field in the X direction, you're going to get a polarization in the X direction. If you apply an electric field in the E direction, you get a polarization in the Y direction, etc. If you don't have spherical symmetry, you could apply, for example, there could be some non-diagonal terms here, so that if you apply an electric field in the X direction, maybe you'd get a dipole moment in the Y direction. So for our case of the CO2 molecule example again, we had the alpha XX and XZ, that was our perpendicular dielectric field being perpendicular to the axis of the molecule, and YY was the parallel to the molecule axis. So that gives us this tensor, okay, with only the diagonal terms. And then if you multiply it out, you get, if you apply electric field in the X direction, polarization and dipole moment in the X direction, in the Y direction, and the Z direction. Okay, now we're going to look at another case where our molecules are what are called polar molecules. So the CO2 molecules and molecules like that, they don't have what we call a permanent dipole moment. You need an external electric field to induce the dipole moment. Okay. Polar molecules like water, like H2O, already have a dipole moment. They have a permanent dipole moment, even without external electric field. So because of how oxygen and hydrogen molecules are configured, there is intrinsic to the molecule a dipole moment. So now we're going to look and see what happens if we put a dipole in an electric field. Okay, so I'm going to place the dipole in an external electric field in the Y direction. So here's my axes. So my electric field here is in the Y direction, and here is my dipole in blue, minus charge and a plus charge, distance L apart. The positive charge will feel a force in the plus Y direction, going in the same direction as the electric field. The negative charge will also feel a force, but it's going to go in the opposite direction, the minus Y direction, going opposite the electric field. And so if we sum the forces on the dipole, we see that we'll get 0, QE minus QE. So that means there's no translational motion that's going to occur in the dipole, in the electric field. But what we're going to find is that the sum of the torques on the dipole moment is not going to equal to 0. So therefore, there will be rotational motion. So let's find the sum of the torques on the dipole. I'm going to use the symbol N instead of tau for to symbolize torque. So torque is our lever arm. If we put the origin at the center between the two charges, the lever arm for the plus charge is L over 2 cross the force, which is this F plus. The lever arm for the minus charge, minus L over 2 cross F minus. I plug in what F plus and F minus are. I have two minuses here in the second term. So I can add these up to get QL cross E. QL, that's just the dipole moment, L being the distance between them. So QL is just a dipole moment of this particular dipole. So the torque is equal to the dipole moment crossed with the electric field. So when the dipole moment lines up with the electric field, the torque is going to be 0. Remember, cross product. So it would be, the magnitude would be PE sine theta. So when the angle between the dipole moments, so when P is pointing in the direction of the electric field, theta is 0, and we get a torque of 0. So what's going to happen is the dipole, if you put the dipole moment at an angle to the electric field, it's going to oscillate back and forth about the electric field. And if there's any friction, it will eventually stop oscillating and line up with the electric field. Okay, so we have polar molecules that have permanent dipole moments and nonpolar molecules that get induced. But in either case, once they get what happens to these dipole moments in an electric field is that they want to line up with the electric field. Okay, so first if we start with a polar molecule, in this case, we have these polar molecules that already have dipole moments, even if we don't place them in an electric field. But because of thermal energy, they're kind of random, they're not aligned. And then we place the polar molecules in an electric field and this aligns them. For nonpolar molecules, if there's no electric field, there's no dipole moment, and there's no alignment, you place the nonpolar molecules in an electric field. First, we get an induced dipole moment in our molecules, and then those dipole moments will line up. So in both cases, the result is that our material gets polarized. And what we'll be looking at in next chapter is the response of the whole material to an electric field and its the material's polarization.